Remember this infinite sum, also known as a series, where we added up 1 over n factorial, starting with n equals 0 and then putting in each consecutive integer. So 1 over 0 factorial, don't forget 0 factorial equals 1, plus 1 over 1 factorial, plus 1 over 2 factorial, and so on. If you added all these up, what is that an approximation of? The natural number e. 2.71828, blah, 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 blah. A series is adding up a sequence. If you take a sequence and you change each of the commas to plus signs, so now it's not a list of terms, but a sum of terms, you have a series. There is something called sigma notation, so that you don't have to write each individual term if the terms follow a certain pattern. So if you had an arithmetic series, then your function right here would be linear. It would look like mx plus b, except not x, it would be I. If your series was geometric, this function would be exponential. This is a capital sigma, the Greek letter, and it is the summation symbol. It means summation. I is the index. I equals, or if your function is a function of n, then this would be n equals, gives you your starting number. And whatever number is up here is your ending number. So if you have an infinity up here, then you have an infinite series. If you have a number other than infinity, then it would be finite. S subscript n is the mean or average of the first and the nth terms. So if I was asked to find the sum of the first 5 terms of the first 5 integers, so 1 plus 2 plus 3 plus 4 plus 5, I would get 15. What if I did that with the formula? That would be S subscript 5, so the 5th partial sum is equal to 5 terms times the first and the 5th term divided by 2. Oh, that would be 15. So let's begin with number 1. We're going to find the sum. First of all, is this finite? Yes, it does not end with infinity. Our formula involves the first term, the nth term, and the number of terms. So let's find that. The first term would be what we get out when we plug in the starting number, the index. Our starting number is 1, so plug in 1 for I. I'm going to call it a sub 1. Remember, a sub 1 represents your first term. Now let's find the 20th term by plugging in 20 for I. And the number of terms from 1 to 20 is 20 terms. Remember, this would not be n if you started at something other than 1. Be careful to notice what your starting number is so you truly know how many terms you're adding. We're taking the sum of the first 20 terms, so we write S subscript 20. That means sum of the first 20. The sum of the first 20 terms is 770. Try part B on your own and then check. And simplify. If you want to, this is still 24 in the numerator and 2 in the denominator, and all a product. So you could divide 24 by 2 to get a coefficient of 12 now. Which makes our sum of the first 24 terms 158. Let's prove the formula to find the sum of a finite geometric series. We know that a series is just adding up a list of terms, or adding up the terms in a sequence. So I could write it as S sub n, the sum of n number of terms is equal to the first term, plus the second, plus the third, plus the fourth, plus ... plus is how you write that in between part, showing we don't know how many terms this is because this is in general form. Then you have the term before a sub n and then a sub n, because this is the sum of n terms. So a sub n would be the last term in that series. Remember, this is talking about a finite geometric series. Also remember, because this is a geometric sequence, each term can be found by plugging it into the explicit rule, where you take the first term and you multiply by the common ratio. A sub 1 is our first term. To get the next term, to rewrite a sub 2 in terms of a sub 1, plug in 2 for n. That's a sub 1 times r to the 1. What would a sub 3 be in terms of a sub 1? That would be the first term times the ratio squared. The fourth term is the first term times the ratio cubed. We write plus dot 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 plus. What about if we plugged in n minus 1? That would be a sub 1 times r to the n minus 2. And a sub n is just the first term times r to the n minus 1. This formula is an equation. It's saying the sum of n terms is equal to the sum of n number of terms, and I can rewrite it as an equivalent equation if I do the same thing to both sides. So what if I multiply both sides by r? You may not understand why, but go with me here. Because we're multiplying each term by r on the right side, each term will now have another r, which means just adding 1 to the exponent of r. So we have a new equivalent sum to our original s sub n. Now that we've multiplied s sub n by r, I want us to write down s sub n before we multiplied it by r. All right, let's subtract. On the left side, I would have s sub n minus r s sub n. If you notice, many of these terms are equal, so when you subtract, you'll get 0. For example, a sub 1 times r to the 1 minus a sub 1 times r to the 1 is 0. A sub 1 times r to the 2 minus a sub 1 times r to the 2, also 0. And we know that since this keeps on going, it will have an a sub 1 times r to the 4, so that will also subtract to 0. And the second sum will also have an a sub 1 times r to the n minus 2, which will subtract to be 0. And all we have left on the right side is a sub 1 and an a sub 1 times r to the n that's being subtracted. So that would be a sub 1 minus a sub 1 r to the n. Now I'm trying to find a formula for the sum, so let's solve for s sub n. Begin by factoring it out on the left side. And to organize the right side a little better, I'll also factor out a sub 1. Divide both sides by 1 minus r. Now we've created a relationship that shows how to find the sum given the first term and the common ratio of a finite geometric series. This formula requires us to know the common ratio and the first term. So let's find that. The first term is what we get when we plug in our index, which is 1. The common ratio is the multiplier, or the base of the exponent. Now this isn't just s sub n because we know how many terms we are adding up. We're adding the first 10 terms. That means n equals 10. So we'll have s sub 10. Now simplify. I'm going to reduce the 4 and the negative 2 to be negative 2 times negative 59,048. So the sum of the first 10 terms of this geometric series is 118,096. This makes sense because geometric means exponential, so your numbers are going to grow pretty fast and the sums will get pretty big. Try part B. Begin by finding the first term, the common ratio, and n, the number of terms we want to find the sum of. The common ratio is the base of your exponent, so 1/2, and we're starting at 1 and ending at 7, so that is a total of 7 terms. Because 8 is being multiplied by this entire fraction, the denominator of 1/2 can be divided from 8 or can be divided from 1 minus 1 over 128. So I'm going to bring it out like this. 8 divided by 1/2 now just times 1 minus 1 over 128.
To do 8 divided by 1/2 is just 8 times 2, so 16, and this would be 127 over 128. Remember, you won't have a calculator for the test. This can help you simplify or reduce as you go. Again, 16 over 128. 16 goes into 128 8 times, so that would be 1 over 8 times 127, so 127 over 8. Can you find the sum of an infinite series? At first, you might say, no, you can't find the sum of an infinite amount of numbers, because intuitively that feels impossible. But is it? Begin by finding partial sums. So if you have an infinite series, any sum other than all infinite terms is called a partial sum. S sub n is the sum of the first n terms called a partial sum. Consider the following infinite geometric series. Find the following partial sums and graph them. Then describe what happens to S sub n as n increases. S sub 1 would be the sum of the first term, so 1/2. S sub 2 would be the sum of the first two terms, 1/2 plus 1/4. S sub 3 is the sum of the first three terms. And it continues on. Let's graph. The sum of the first term is 1/2. The sum of the first two terms is 3/4. The first three terms is 7 over 8. As a decimal, that would be 0.875. So I wrote down the decimal approximations that I've been saying, and for the rest of them to make it easier to graph. So at 4, we have 0.937. At 5, the point is 0.968. As we add more terms, it doesn't feel like we're getting closer to infinity. It feels like we're actually getting closer to a number. It feels like our sums are approaching the number 1. Would they ever go over 1? Look at this pattern, 15 over 16, 31 over 32. What would the next one be? 63 over 64? As we add more terms, the sum keeps getting closer and closer to 1, which means that as n approaches infinity, S sub n approaches 1. Given this infinite series, I want you to evaluate a sub 1 divided by 1 minus r. Well, a sub 1 would just be 1/2, and our common ratio is 1/2. Anything divided by itself is 1. Seems to give us the infinite sum, or the sum as n approaches infinity. Let's look at the process we did for a finite geometric series. I replaced each individual term with the explicit formula of first term times r to some power. Now we're going to multiply this one by r to get an equivalent infinite series. Remember, multiplying the same base just means adding 1 to the exponent. So r to the n times r is just r to the n plus 1. R to the n minus 1 times r is r to the n. Now rewrite the infinite sum that wasn't multiplied by r in the space I've left between. And let's subtract. Again, we have the same terms. When subtracted, will become 0. It's not shown here, but I know that a sub 1 times r to the 4th is in between this plus ... The a sub n minus 1 times r to the n is between this plus ... And you may think we still have this term at the end, but no, these are infinite series. So the infinite number of terms here will eliminate to 0 with the infinite amount of terms here, which leaves us a sub 1. Factor out s sub infinity, or the infinite sum, and solve for s sub infinity. The sum of an infinite geometric series is a sub 1 divided by 1 minus r. Or you could write it as just sum, so if there's not a little subscript there, then I know it's an infinite sum. And then a would represent whatever the very first term is. That could be a sub 0, that could be a sub 1, depending on your index. Now, you can't find the sum of every infinite geometric series. Something that has true exponential growth would not make sense to be able to find the sum of. That would just go to infinity. But something that has exponential decay, that kind of multiplier would give you an actual sum to your infinite series. So that multiplier, or common ratio r, the absolute value of it has to be less than 1. Remember, for a series or a sequence, r can be negative. If the absolute value of r is greater than or equal to 1, then the series has no sum. So let's use our formula. Find the sum of each infinite geometric series. If there is no sum, explain why. First, check the common ratio. The common ratio is 0.7. Is the absolute value of 0.7 less than 1, or is it greater than or equal to 1? Well, the absolute value of 0.7 is 0.7, and yes, that is less than 1. So for this infinite series, there is a sum. Find the term you get when you plug in the index of 1. If the index is 1, then this will be a. If the index were 0, then a would not be so obvious. Plug it into the formula a over 1 minus r. So our infinite sum of this geometric series is 10. That's so crazy. We can add up an infinite amount of numbers but get a finite result. So cool. Let's find the common ratio for part B. That looks like 3. Is the absolute value of 3 less than 1? No, it is not. Because the absolute value of our common ratio is not less than 1, this infinite geometric series does not have a sum. Let's find the common ratio for C. Well, 1 times what gives me negative 3/4? Looks like negative 3/4. And then you check the other ones, and yes, the common ratio is negative 3/4. Now, is the absolute value of negative 3/4, is that less than 1? Absolute value of 3/4 is 3/4. And yes, 3/4 is less than 1, which means this infinite geometric series has a sum. A would be the first term they gave us, 1 over 1 minus 3/4. Wow, the sum of this infinite geometric series is 4. Write 0.242424 repeating as a fraction in simplest form. What? First of all, let's write this never-ending but repeating decimal as a sum. What do I mean? This is equal to 0.24 plus 0.0024, 0.00024, and we continue on. Now I have an infinite series. The first term of that infinite series is 0.24. The common ratio, you can always calculate the ratio by taking one term and dividing the term before. Our common ratio is 1 over 100, or 0.01. Let's find the sum of this infinite series. If you can't immediately see, you can multiply this by 100 over 100, which would move those decimal places and give you your final fraction of 24 over 99. Isn't that cool? Before, you used to know how to turn a fraction into a repeating decimal, and now you can turn a repeating decimal into a fraction. And that is our summary of series.